Could everybody see the screen? Yes?
Yep.
Okay, good. All right, let's start the recording. All right, so we're moving on into chapter 8, which is basically applications of integration. It's actually one of the reasons why I didn't really test you on chapter 5, because chapter 5 was just basically word problems, and we're going to cover that in chapter 8 anyway. So chapter 8 is going to look at arc length, surface area when we're revolving around an axis, and then we're going to look at some engineering and medical or biology type problems on how we can actually use calculus to solve some of those situations. So tonight we're going to look at arc length, which is really important when we're starting to look at surface area and stuff in the next one. So if we're looking for the length of a curve on a circle, it's pretty easy. That's just perimeter. If we're looking for the length of a straight line, again, that's really easy. But when we're trying to look at a curve that goes like a roller coaster, it's a lot more complicated to do. So to figure that out, we need to come up with a formula to do that. So when we're looking at the, this is where we're looking at finding it for the circumference of a circle. And this is actually how they originally did it way back in the Pythagorean times and Greek times. They were able to figure out the square, and then they wanted to keep going to find the perimeter, and eventually they actually ended up coming out with the 3.1415, and it keeps going. When they originally came up with it was just 3, and then every iteration they got a little more accurate to it. And back then they actually didn't use decimals; they just used smaller and smaller lengths. So when they got to 3.1 that we call it today, it was actually 31 lengths of their decimal type unit. So that's how they actually figured out the pi and the circumference of a circle. So we know how to do that, and we're able to use a formula for that. When we're going to use the same concept really when we're looking at a curve. We make straight lines. And as we know from integration gets those lines closer and closer and closer together. So the first formula I'm going to show you is the wonderful Riemann-Sum version of it using limits. And then when we're looking at that, we also have to we're looking for basically the distance between those 2 points. My distance formula is x2 minus x1 squared plus y2 minus y1 squared. It's kind of like the Pythagorean theorem. So it's the change in x squared and then the change in y squared. And then we take the square root of that. So that's my distance formula right there. So we're going to use that to come up with our formula for integration. So we have that one. Now we're looking at, so y is really my f of x. So the change in y, that's going to be my f prime of x squared. And then we can just get rid of the x because that's going to be a constant. So that comes out, and that's going to become my change in x, or my dx. So I have 1 plus the derivative of f of x squared times the change in x, which is my dx. So my integration formula, the one that we're going to actually use, is integral from a to b, square root of 1 plus the derivative of f of x squared dx. So that's going to be the formula I'm going to use to find my arc length, is right there. And the square root always makes things a little more complicated when we're doing integration. All right, let's actually use this to do a problem. All right, so the first one, I want to find the length of an arc on the parabola y squared equals x to the third. So notice it's not even in function format, so we're going to have to change that there. And we're looking at it from points 1, 1 to 4, 8. So they're always going to give you your 2 points, the x's and the y's, because depending on how you solve it, we could use either one of those. So you have to choose which way you want to solve it for, and then choose which points we're going to use, or which values we're going to use for a and b. If we look at the picture here, this one's on the positive side up here. So what I do, if I wanted to do the square root to get rid of that 2, I only have to worry about the positive version of it because my points are all the positive sides. So for this one, the easiest way to do this one is we're going to solve this one for y. So I have y equals x over x to the 3/2 power by just taking the square root of both sides. Notice I'm leaving it as a fraction. It makes life a little bit easier, so I'm not dealing with the square root symbol. We now need to know the derivative of that because remember, it's the derivative of the function. So the derivative of that, the dy over dx, is 3 over 2 x to the 1/2 power. So now we can plug into my arc length formula. We're doing it in terms of x. So we're going to use my points, the x values of my points, which was 1 and 4. It's the square root of 1 plus the derivative squared. So that's where the 3 over 2 becomes 9/4. And the x to the 1/2 just becomes x. So I have the square root of 1 plus 9/4 x dx. Questions up to there? We good so far? All right.
Good.
Okay. All right. So now for this one, since we have something inside of the f of x there, we're going to have to do the u substitution. So we have got the u, we're going to set the u to be the 1 plus 9/4 x. So du is just 9/4 x. I don't have the 9/4, so I've got to kind of move it over. The other thing I want to do is I want to change my values here, the 1 and the 4. So this way I don't have to worry about going back to the x after I do the integration. I can just leave it. So we plug in the 1 and the 4. When we plug in the 1 to this, I get u as 13/4. And when I plug in the 4, I get u as 10. So my new integral that I'm going to solve is 4/9, the integral of 13/4 to 10, square root of u du. So I've changed my range or my domain or the values for my integration, the 13/4 and the 10. The 4/9 came from that 9/4 dx when I had to solve for du. And then the u is the square root. So we do the integration of that. The integral of square root of u is 2/3 u to the 3/2. And multiply that by the 4/9 up front. So we can take out my constant, which is 8/27, and then we're plugging in 13/4 and 10. So 10 to the 3/2 is 10 square root of 10. And 13/4 to the 3/2 is 13 square root of 13. And we multiplied by the 8, or well, it was over 8. Multiplied by the 8 to get rid of that. So it's 1/27 8 square root of 10 minus 13 square root of 13. And that would be my arc length. And that's as far as I want you to go. They don't want it as a decimal. That was one of the things I noticed some people were asking on the test. Unless they specifically ask for a decimal answer and tell you what you're rounding to, they want an exact answer. So you want to leave it as square roots, you want to leave it as the LNs. Pies are fine for when you're doing thetas. So can we put it there? No, they don't. So one of the nice things, if we look at this, if we just did the distance formula from, actually, I'll show you this. So if we did just just did the distance formula, and we were doing it from 1, 1 to 4, 8. So 1 minus 4. So we get the 7.615. That would be the answer if I just did the distance between those 2 points. And if we did what we just got, the answers do come out to be pretty similar in values. And the one we got is a little bigger, and that makes sense because if a straight line, my arc was underneath it. So if we go back and look at the curve, you can see if I drew a straight line from that to that, it would be above the line. So the line would be a little bit longer for that. So that value makes sense when we do it. And that's something else you can look at when you're doing it. If as long as the curve's not really crazy, you can look at those points and say, okay, does my answer make sense for the value I got? So sometimes it's just as quick as plugging the numbers in to see if it makes sense. All right.
Is the answer wrong if you don't put it in that square root form at the end?
It depends on which. You have to leave it with the square roots. They didn't want it as a decimal. So if you changed it down to 7.633, then yes, it would have been wrong.
What if you leave it as the 10 to the 3/2 minus the 13?
That would have been fine. I would have accepted that answer. Because that's still, it's not written out with the square roots, but it's still a completely done answer. And there's not much you can simplify or combine things at that point.
Okay.
So I'd have accepted that answer. Honestly, a lot of that just comes down to teacher preference at that point. Some people like everything really nice and neat. As long as the answer comes out to be the same, it doesn't really matter to me. All right, let's look at another example of this. So this one, we're going to find the length of an arc of the parabola y2 equals x. Shoot, hold on. Bad pen. Okay. All right, so I've got my x equals y squared. So I'm going to do in this case, since I'm doing it, I have the x, so this is going to be dx over dy. My derivative of that would be 2y. So then we're going to plug into my formula. So I have the integral. Now we're using the y values, but in this case, it doesn't really matter because they're the same as the x and the y. So it's 0 to 1, and it's the square root of 1 plus the 2y squared, which would be 4y squared. And it's dy. All right. So how am I going to do the integral of this? So I have the square root of 1 plus 4y squared. Think back to chapter 7. That stuff's never going away. What did we do when we had the square roots with addition or subtraction inside of them? What was the key thing we used to do for those?
Trig substitution.
Yep, we have to do the trig substitution. So this one we're going to make, we're going to set y to be 1/2 tangent theta. Because that's going to get rid of my 4, so I don't have to worry about the 4 in front. So I'm going to be able to do my quick substitution. So dy is 1/2 secant squared theta, d theta. And then, so I can do my square root of 1 plus 4y squared ends up becoming, when I break it all down, just secant theta. So the next thing, since we're doing this as exact values, we can leave the 0 and the 1 there, except then I would have to take whatever I have at the end and go back to x's, which might make a little harder to do. So let's change those over into theta since we're doing exact values. So I've got y equals 1/2 tangent theta. So if y is 0, 1/2 tangent theta, that means tangent theta is going to be 0, so theta is 0. Now, if y is 1, that means it's 2 equals tangent theta. So that means tangent -1 of 2 equals theta. So my integral that I'm going to do is 0 to tangent -1 of 2. And then it's, take the 1/2 out. It's secant to the 3rd theta d theta. Questions on how I got any of that? So remember, the square root becomes secant theta. The dy was 1/2 secant squared theta. So that's where the secant to the 3rd came from. All right, we actually did this example way back in section 7.2. You actually do this one by integration by parts, but I'm just going to actually do the integration because we're going to come up with the answer faster this way instead of me doing out the whole integration by parts again. So we end up getting 1/4. And it is secant theta tangent theta plus ln secant theta plus tangent theta. And we're evaluating that from 0 to tangent -1 of 2. All right. So we're plugging the values in. We know it. We're looking for tangent of theta. And I know tangent of theta when I'm plugging in. So I've got tangent theta equals 2 for that part there. So we could actually use that information to do some of the stuff. So the 0, secant of 0 is yeah, we plug in 0, you're going to get tangent of 0 is 0, so that cancels that part out. And secant of theta is, or secant of 0, I think is 1 if I remember right. Yeah, secant of theta is 0. Secant of 1 is secant of 0 is 1. Yeah. I can speak tonight, I swear. All right, so that basically, this first part cancels itself out because tangent of 0 is 0. And the second part, we end up getting ln of 1. And ln of 1 is also 0. So the whole 0 piece cancels itself out. So now I got to figure out what secant is and what tangent is. So I know tangent of theta equals 2. So those are all the 2's. And I also know that secant theta, or secant squared theta, or equals 1 plus tangent squared theta. So that means secant squared theta would be 5, and secant theta would be the square root of 5. Does that part make sense? How we found that? So now if we plug all this in, I've got 1/4. This first part is going to be 2 square root of 5 plus the ln of square root of 5 plus 2. And that's my final answer. So that's really the hardest part of all this stuff is you still have to remember all the actual rules that we were doing from chapter 7. Which is one of the nice things about that is we go to the final exam, you're going to constantly be using those rules, so you're not going to forget them by the time the final exam comes around. But it's also why I want to make the review of the test that you guys did yesterday, because I think those are really going to help you to remember how to do a lot of that types of stuff. So, all right. So the next thing we're going to look at is known as the arc length function. So what we did a second ago is we did the arc length formula. It basically came up with exact values. The only difference between that and the arc length function is the arc length function goes from a starting point to x. Basically, it allows me to come up with an equation or a function that I can plug in any value to it and find the actual arc length of that function. So we do it once, and then you can plug in multiple values to figure out the arc length. So it makes it a little, it basically ends up giving us an answer at the end that's not an exact answer. It gives us a formula at the end. So when we're looking at it at the end, that s of x, notice how we're doing it as in terms of the derivative of f of t. Since we're plugging the x back in, we just changed the letter, the variable in it, so this way we can plug the x back in at the end. It doesn't really make a grand scheme of difference because you're going to plug the number back into it anyway. But it just saves the confusion with the x's and whatnot, because the value you're getting at the end is not the exact same as the x at the very beginning of the problem. So it kind of separates them a little bit. So you'll see that when we go through the next example. All right. Actually, you know what? We're going to do this one out. All right. So we want to find the arc length function for y equals x squared minus 1/8 ln of x. And we're starting at the point of 1, 1. So the first thing I've got to do is my f of x is x squared minus 1/8 x, 1/8 ln of x. So my f prime of x, so the derivative of that, is 2x minus 1/8x. So then my 1 plus that squared, so 1 plus f prime of x squared is 1 plus 2x minus 1 over 8x squared, which we can FOIL out the squared, and we get 1 plus 4x squared minus 1/2 plus 1 over 64th x squared. Now, if we combine some of this stuff and rearrange it a little bit, so we get the 4x squared plus 1/2 plus 1 over 64 x squared. So we're going to have to do the square root of this. So if I can factor this so that it comes out to be something squared, it's going to make my lives a lot easier. And then this one you actually can. So this one, the 4x squared is 2x, and the last one is 1/8, 1 over 8x squared. And if you multiply those out, you're going to get the 1/2 in the middle, which kind of works out nice. Doesn't always work. Sometimes we have to do a little more calculations for this one, but they pick examples that work out pretty nice most times. So I'm going to do the square root of that. So I'm doing the square root of 1 minus f prime x squared. So it's the square root of that. That's just 2x plus 1 over 8x. So far we haven't done any actual integration. All we've done is simplify everything down inside. So when I do my integral piece, I'm literally just going to be looking at that part there. So it just makes my integral piece a little bit nicer to look at. So we're going to change the color. So now my arc length formula, the s of x, is the integral from 1 to x of, in this case, we're going to do, it's 2t plus 1 over 8t dt. So we do our integral, and we get t squared plus 1/8 ln of t, and we're evaluating that from 1 to x. So if we plug 1 into that, we get just 1. And we plug in x, so we get x squared plus 1/8 ln of x, and it's minus 1. This is my final answer. So that would be my arc length formula, or arc length function, for y equals x squared minus 1/8, starting at 1. So now if I wanted to find the arc length to go to, say, 3, which they do, we can just plug 3 into that function, and we get our answer out. If I wanted to find it to 4, I could just plug 4 into that answer and find it out. So believe it or not, one of the big uses of this is actually in video games. When they're looking at projectile paths, it's all dealing with arc lengths and how far things have to go, the speed based on it. And since everything's always variables in that, the computer can't have exact values of those lengths, so it's got the formula built into it to do the calculations to figure all that stuff out. So, all right. Questions with either of those? Okay. All right, we're going to do a couple of, we're going to do an example of each one of them. Just a little, I'm going to give you a little bit of time to figure out do part of it, and then we're going to do it together. So this one's asking you to find the arc length of this problem. So Remember, we're going to use that formula. So we're doing the arc length. In this case, we're going from 1 to 9 of the square root of 1 plus f prime of x squared d, or sorry, of y squared dy. All right, so take a few minutes, work that one out, and then we'll go through and do it together. and I'm talking to myself because I didn't put down my mic. So the first thing we're going to do is change the x into two terms instead of product of factors. So we get rid of the parentheses by distributing the 1/3 y square root of y. And we get 1/3 y to the 3/2 minus y to the 1/2. Then we do the derivative of that because that's pretty easy now. And we get 1/2 y to the 1/2 minus 1/2 y to the negative 1/2. So now we're going to go through and do the inside of the square root, clean it up. So we got 1 plus that squared. So we FOIL out the derivative that we just got there. We get 1 plus 1/4 y minus 1/2 plus 1/4 y to the negative first. Put the y and the 1/2 together, you end up getting 1/4 y plus 1/2 plus 1/4 y to the negative first, which then actually factors down to be a perfect square. So it's 1/2 y to the 1/2 plus 1/2 y to the negative 1/2 squared. So when we plug it into the square root, it gets rid of that. So my integration is going to be a little bit nicer to deal with. So I have the integral from 1 to 9 of 1/2 y to the 1/2 plus 1/2 y to the negative 1/2 dy. So when we do the integral of that one, we can take the 1/2 out. It's on both of them. And we get 2/3 y to the 3/2 plus 2y to the 1/2. And we're evaluating that from 1 to 9. So I've got 1/2, 2/3. The 9 is going to be 27 plus 6. And then it's going to be minus 2/3 plus 2. So do all the arithmetic out, and you end up getting the final answer is 32/3. After you do all the arithmetic out. So that would be the arc length of that curve. So a lot of this one ends up coming down to the algebra and everything else and the manipulation of the equation before you even get it into the actual integral. You want to try to make the problem as simple as you can before you do the integral part of it. It's one of the things that, and I don't remember if your teachers actually told this or not, when you're doing like the quadratic formula, you know, that big long formula, the negative b plus or minus the square root thing. I always do the part underneath the square root, the discriminant first, because it makes that nice and easy just to deal with that. Plus you find your values and then you plug it in. So instead of having to write the square root out a million times, you just do it once. Same thing here. You don't want to do the integral of the big piece at the beginning and have to do all the manipulation inside that integral. Deal with all that stuff first and then do your integration part of it. So. All right. One more problem we're going to do.
So
yep, go ahead.
On the left side of the equation, at the bottom there, so you're just factoring out what's above it?
Yeah, so the 1 and the 1/2 goes together to gives you 1/2 in the middle. And then, yeah, you're factoring it. So you have 1/4 y plus 1/2 plus 1/4 y to the negative first. And when you factor that out, you end up getting the 1/2 y to the 1/2 plus 1/2 y to the negative 1/2. A lot of times, so the first thing when you're doing these problems like this, and you get something that looks like a quadratic, the first thing you try to do is take the square root of both ends. So like if you take the square root of 1/4 y, you get 1/2 y to the 1/2. take the square root of 1/4 y to the negative 1, you get 1/2 y to the negative 1/2. And just see, like, you could, if you FOILed that out real quick, just see if you get 1/2 in the middle. So like if you were to multiply those two together, you get 1/2. The y's are going to cancel each other out, so you get 1/2 and 1/2, which is 1/4. And you do the opposite of that once you get 1/4 plus 1/4, which gives you the 1/2 in the middle. So it's like, that's just a nice little, it might not always work, but that's going to be the first thing you're going to want to try when you're trying to do a perfect square like that. And if it doesn't work, then it's not going to go out to be a perfect square and you're going to have to deal with something else. So, and not all these problems will come out to be perfect squares. A lot of them do, but just because they picked them so that they actually work out kind of nice. All right, let's do a function one. All right, I am going to give you one thing because so this way you don't have to look it up. The derivative of sine -1 of x. So y is that. So y prime is 1 over the square root of 1 minus x squared. That's the derivative of it, in case you didn't remember it. So this way you don't have to go look it up.
Would 1 minus x square root of 1 minus x squared, would that be secant?
No, you're doing the derivative, not the integral.
Oh, okay.
So you would have to do secant if you were doing the trig substitution, but that's when we were doing integration. You have to do chain rule for that one.
Oh, okay.
Just check and make sure you got your derivative right. I just did that on the screen. And as long as you got that part right, go down to simplifying it and working it through.
Did you say you put up the whole derivative or just the derivative of sine? The
Nope,
inverse
I put
sine?
up the green underneath it's the whole derivative.
I don't see anything under it.
Yeah, no green.
It's weird. Because I see
Okay.
it on my screen. Is it there now?
Yeah.
Okay. That's what happens when you sit still in a computer room too long. The lights go out.
Yeah. How did you know that it was from x to 0?
You're muted again.
You're muted.
Sorry, I was muted the entire time I was writing that. So the original starting point was 0, 1. So that's why it started off at 0.
Yeah.
And we're always doing it to x when we're looking at the for the arc length function.
Oh, okay.
So it's always going to be 0, or it's going to be whatever starting point they gave you to x. So and we did a quick u substitution to get the when we had the 1 over 1 plus t, the square root of 1 plus t. That's how we got rid of that part. I got to get my mic from my classroom because it's got a little light on the screen that I just tap it. This one I keep forgetting I put up the mic on my headset. And I put down the steps down below if you needed those to see how it got down to the 2 over 1 plus x. There was a bunch of little steps there.
In the second step, in the red.
Yep.
Did you do a u substitution for 1 plus
Yeah.
t?
Yep.
Okay.
So yeah, you do the you make u 1 plus t, which ends up becoming just 1 du. So we don't really actually have anything of that. So it's just 1 over the square root of u, which gives you the square root of 1 plus or square root of u, 2 square root of u on the top. And then you plug back in the 0 and the x to get the final answer. All right.